So what are you aware of that's in the nucleus? And we know that there's a small, dense positive nucleus, right? And somehow the electrons are outside that nucleus. We're going to get to that a little bit later. So what are the things that are found in the nucleus? What's that? Protons. And what else? It's in the nucleus. Protons were found first. Once we knew that the nucleus existed, that was what was detected first. So protons, what kind of charge do they have? Positively charged. And we should also note that it has the same magnitude of charge as an electron, right? So a proton and electron will cancel each other out in terms of charge. One proton cancels out one electron in terms of charge. Okay. In terms of size, though, it's a lot bigger than the electron. Okay. In your book on page 76, they kind of have a table up at the top that just relates each particle that's in the atom. So you can kind of compare the mass compared to each one of them. But we're going to talk about something called mass number. And what mass numbers are is it's just the number of particles that, like if you look at the mass number of an isotope of an element, it's the protons plus the neutrons because they make up the mass of the atom. Electrons are so small that their mass is negligible. So an electron's mass number would actually be 0. So electron mass number is 0. Because its mass is so negligible. So physicists will tell you that electrons have no mass, but that's not possible, right? It's just that it's such a small mass that we don't even take it into consideration when we're looking at the masses of the period. And I believe the protons were also discovered by Rutherford just a little bit after he discovered. So the other thing that's part of the nucleus then is the neutron. And that took a while till it was discovered. I think that was like 1932. So really in perspective of where we are today, that's not all that long ago, right? Don't quote me on that, but it's around there. And that was discovered by scientists named Chadwick. And why do you think it took a little bit longer for the neutron to be discovered? What do we know about the neutron? Right, there's no charge, so there's no way to detect it in terms of charge, but it does have a lot of energy. So that's actually how they detected it, because it has energy. That's where that joke comes, where the neutron goes into the restaurant, orders a meal. After he's done eating, he asks the waiter, how much do I owe you? He says, for you, there's no charge. You get lots of bad jokes. All right. Neutron also has a mass number of it's a slightly larger than a proton. And when you look at its total mass, it's actually if you would look at it in grams or whatever, the mass of a neutron, it's actually the proton's mass plus an electron's mass. So we now know today, and I'm not super knowledgeable in this, but we know that they're made up of quarks. And I'm not overly familiar with quarks. You got more into that if you study physics. But we now think that subatomic particles are made up of even smaller particles called quarks. And the quarks that make up a neutron are pretty much equivalent to the quarks that make up a proton plus the quarks that make up an electron, which would then make sense that they're neutral, right? Because if you're putting a proton together with an electron, their charges would cancel out, right? And if you're merging that all together into one big particle, one slightly bigger particle, I should say, to get a neutron, it all kind of adds up. Right? So if you add up the mass of the quarks of a proton plus the mass of the quarks of an electron, you pretty much get the mass of a neutron. Does that make sense? And that's why it's neutral, or it doesn't have any charge to it. Okay. So then once we discovered neutrons, we also realized that one part of Dalton's theory, the part where he said that all atoms of the same element are identical in every way, that's not true. We have to modify that a little bit. Okay. Remember, Dalton thought that the atom was the smallest particle, right? That everything was made up of atoms, and atoms were the smallest thing possible. Now we realize that atoms are made up of protons, neutrons, and electrons, right? Because we discovered electrons, we discovered the nucleus, we discovered the particles that are in the nucleus. Now we also started to realize that atoms of the same element aren't always identical, okay? Where we have isotopes. What is different about atoms or isotopes of atoms? What is it that's different? I don't know if we just talked about isotopes in the past. What's different about isotopes of an element? What is it that's different? They're the same element. What has to be the same about them is their atomic number. What does the atomic number tell us? Look at the periodic table, we see that they're ordered by atomic number. Right? What does the atomic number tell us about atoms? Anybody know?
Number of protons?
That's the number of protons. And so isotopes, they're atoms of the same element. They have the same atomic number. That can't change. If you change the number of protons, you get a whole new element. So what's different about them is they have different mass numbers. And what the mass number is Mass number is the number of protons plus neutrons, because that's what makes up the mass of an element or of an atom. So really what's different about them? If they have the same number of protons, what must be different about them? Neutrons. So atoms of the same element can have different numbers of neutrons. And that's what makes them isotopes. Okay, the number of protons doesn't change. That has to stay the same or it's completely different. So we have to have a way to differentiate between different isotopes, because sometimes we use one isotope for a purpose that we can't use another isotope for. For example, there's radioisotopes. Radioisotopes are radioactive isotopes. They're the ones that, for some reason, the number of protons and neutrons combined in the nucleus makes the nucleus unstable. Okay, there's a certain ratio between protons and neutrons that has to exist in an atom to keep it stable. Otherwise, it's going to decay radioactively until it becomes something stable. And radioactive decay means it's giving off part of its nucleus. It might give off a neutron, might give off an alpha particle, which is 2 protons and 2 neutrons together. Might give off what we call a positron, which comes from the decay of a neutron. Those types of things. I think I'm going to contact Advancing Science, like I said, to do some nuclear labs, and that way we can explore that a little bit more, learn a little bit more about radioisotopes. Okay. But for right now, we're just going to look at how do we distinguish between different isotopes. So there's different ways that we can distinguish, because on the periodic table, that just lists all the elements, okay? If we listed every single isotope of every single element that's up there, the thing would be too complex, so it would be hard to use. So we kind of have to just have a way of telling what different isotopes there are. So there's different ways that we can represent different isotopes. There's a symbol notation. And that's where you just put the element symbol. I'm just going to put X there. So X represents the element symbol from the periodic table. So like for hydrogen, it would be H, for oxygen, it would be O. Okay. And for some reason, for atomic number, they use the letter Z. And for mass number, they use the letter A. I honestly don't know where those symbols come from. But if you ever see like Z equals 8, they're saying the atomic number is 8. Okay. So A stands for mass number. Z stands for atomic. So you put the element symbol, and sometimes you won't even see the atomic number because they assume that they're giving you the symbol of the element. You can look on the periodic table and find the atomic number. What you won't find on the periodic table is the mass number. Okay. What these masses are, I think you're all familiar with the fact that there's masses up here, right? So these are average masses. These are average of all different isotopes. So since we can't put all the individual isotopes in here, it's called transporters, right? Some elements only have 1 or 2 isotopes. Okay. Other elements might have 15 isotopes. So we can't just list them all. So these numbers up here, this is an average mass. And the way they get that is they get it by doing a weighted average, kind of like when you have a class that does a weighted average of tests, quizzes, and homework. So your tests are usually like 70% and quizzes 20%, homework 10%. So the tests are going to have the biggest impact on your grade, right? with isotopes, whichever one is most abundant, usually there's one isotope that's much more abundant than the other ones. So that's going to have the biggest influence on your average mass. That's the average. So that's one way to distinguish it. And I'm going to show you an example of hydrogen. Hydrogen actually has 3 isotopes. There's also a hyphenated notation. Where you would just write out the element's name and then put its mass number behind it. Or you might see the symbol. Sometimes instead of the name written out, it's the element symbol written out, just with a hyphen and then the mass number. Again, because you can look up on the periodic table and find its atomic number, if you know which element it is. So in this one, they just completely ignore the atomic number. Like I said, sometimes it's ignored here too. So you might see an element symbol just with the mass number. So if we look at the isotopes of hydrogen, for example, so I'm just going to do the 3 isotopes of hydrogen. I just made a little chart. I'm going to put its symbol notation, its hyphenated name. I'm going to list the atomic number, the mass number, the protons, neutrons, and electrons. Okay. So there's 3 different isotopes of hydrogen. Hydrogen is number 1 on the periodic table. So what would the protons all have to be? If its atomic number is 1, how many protons does each isotope have? Hydrogen, 1, right? Whatever the atomic number is, in this case is 1, the protons have to match that because the atomic number is the number of protons, right? And as long as it's a neutral atom, okay, as long as it hasn't formed an ion, which we'll get to a little bit later, how many electrons would it have to have? Okay, if it's a neutral atom, so if it's neutral, that means it has no charge overall, right? So if it has 1 proton, how many electrons would it have to cancel that out? 1, right? So right off the bat on these tables, it's pretty easy to fill in a few of the tables, unless you have ions. Ions means that there was a loss or gain of electrons, which we'll get to that with bonding, okay? But as long as the overall charge of the atom is 0, as long as it's neutral, your protons and electrons have to equal each other because their charge has to cancel out. Right? So there's three different isotopes. Let's draw some lines here so I'll jumble up. These are the 3 symbols. Okay, or the 3 different, the symbols for the different isotopes of hydrogen. There's 3 different isotopes of hydrogen. There's an isotope of hydrogen that has a mass number of 1, one that has a mass number of 2, one that has a mass number of 3. Okay. So right there, we just gave the mass numbers, right? Mass number is A. So there's one hydrogen isotope that has a mass number of 1, one hydrogen isotope that's mass number of 2, one hydrogen So if my mass number is 1, and we just said mass number is protons plus neutrons, right? 1 plus what gives me 1? 0. So one of the hydrogen isotopes has a mass number of, or it has 0 neutrons, doesn't have any neutrons. So basically what it is just a proton surrounded by an electron. There are no neutrons. That's actually the most common. That makes up most of hydrogen. Then there's hydrogen that has a mass number of 2. So how many neutrons would it have to have? Protons plus your neutrons have to add up to the mass number. 1 plus what gives you 2? Simple. And if it has a mass number of 3, how many neutrons was it? 1 proton plus how many neutrons? Okay. And then the name's easy. You're just going from the symbol of the name. You're just naming it followed by its mass number, right? So this is just hydrogen 1. This is just hydrogen 2. That's its technical name. Now there are some isotopes where they give common names as well. Okay, so this one is protium, deuterium, and tritium. But not all isotopes have common names. I'm just going to put that in. Just in case you ever come across these names. You don't have to memorize this, but I'm only going to go by the technical names, hydrogen 1, hydrogen 2, hydrogen. It's just that there are some elements that have common names for isotopes. For example, too, like where this hydrogen 2 is used, where they isolate hydrogen 2, they make water out of it, and they call it heavy water. That's used a lot of times in nuclear plants. Because in a nuclear plant, what you have to do is you have to have something that's giving off neutrons. You have a source that gives off neutrons. And you're trying to get those neutrons to absorb into the uranium nucleus. And then when that happens, it makes the uranium split in 2. And it gives off a huge amount of energy, and that's where we get nuclear energy from. But that neutron can't move too quickly, so it has to move through what we call a moderator to slow it down. Sometimes they use heavy water as the moderator. In other words, they make all the H2Os using deuterium for the hydrogens, making it a little bit heavier than normal water, which is mostly hydrogen 1s. Because hydrogen 1 is the most of them. Questions on that? And then that's what you do with different devices. Did you ever hear of carbon dating? What's that? Dating? Carbon dating? I wouldn't suggest you go through carbon dating. It's a little bit unstable. All right. So what do we use carbon dating for? Right. And it has to be a living thing, right? Living things are made up of mostly carbon. So when we're trying to see like how long ago that thing has been around, okay, carbon-14 is an isotope that's in all living things. So when that living thing dies, the carbon-14 gradually just keeps decaying, right? So you can take a sample of the carbon and figure out how old it is, because it has this thing called half-life. Did you ever hear of a half-life? We'll talk about all this stuff. We're going to do a little bit of radioactivity in the lab. But half-life is how long it takes half of the sample to decay. And then another half-life, half of that half will decay, so it'll be down to a quarter. So you can keep going back through and seeing how old something is. Now, it's only good for so many half-lives. After that, it gets because there's so little left, you can't really make a good prediction. But carbon-14 has a half-life of 5,700 years. So if we can go back 4 or 5 half-lives, that's a pretty long time, right? So we can kind of date how long something that was organic was around. Okay, so living things we can kind of detect. For the Earth, we use uranium because we have uranium deposits on Earth. And uranium's half-life is like 9.1 billion years. So we can pretty much date back to when the Earth was formed because the uranium deposits we have, we can figure out how much has decayed and then figure out how old the Earth is. And it's not an exact science, but it's very, you get a very close estimate. So just to come, we'll just look at carbon-14. The most abundant carbon is carbon-12. Okay, carbon-12 is very stable. That's the most abundant isotope of carbon. But these are 2 common isotopes of carbon. There's more isotopes. But let's just fill in the chart for this. So see if you can do that on your sheets. Just do the carbon-14 and carbon-12. Fill in the rest of the columns there. I gave you the symbol. Down the name, atomic number, mass number, protons, neutrons, fill it in just like you did for hydrogen. What's the name of this one going to be? What's the name of this one? Okay. Well, we know the mass number and we know the atomic number, right? So my atomic number is the C, right? That's the same for both of those, right? This mass number is 14. This mass number is 12. And what did we say the atomic number is the same as? Protons. It defines the number of protons, right? And since we're talking about neutral carbon, how many electrons must we have to cancel out those 6 protons? I'm doing the electrons, but you're right for the neutrons, right? So then the neutrons, the protons plus the neutrons have to add up to be the mass number, right? So this plus this, let's do that. 6 plus 8 gives us 14. So how many neutrons are in carbon-12? 6. And they actually use carbon-12 as the reference for all of the masses on the periodic table. Because it has 6 of each particle, they just divide that by 12, which is the ones that give it its mass. And that's how they come up with its, the mass that they relate everything to, the relative mass. Any questions on that? All right, so we'll stop there. Bell's about to ring. We do have the retest tomorrow if you're planning to take it. If you're not taking it, I do have an activity on isotopes that I'm going to be putting out. So those who are not taking it, start on that. And then as you finish the retest,